Yes, both of us, Wyatt. All right. So, yeah, make sure it's not like a public office.
You don't want to
We
be
can get
famous?
rich.
Yeah, you could get rich.
I didn't do makeup today, so it's really not a good idea. What's that? No.
Not because I just don't want to do it, but I left my computer.
Okay, so no, you just look along.
I'm just gonna stay.
Good job.
Okay, this, thank you for clarifying that. It's like, at first I thought he said, I just don't want to do it, but I realized he said, it's not that I don't. All right, here we go. Get the temperature. This equation relates to temperature given in X degrees Fahrenheit. So when we plug in Fahrenheit, what does it calculate? Celsius. So what we're going to do, or what you were supposed to do yesterday, is take this equation and rearrange it so that it will allow us to plug in Celsius and output Fahrenheit. So to do that, we just get X by itself. So how do we get X alone? Divide by 5/9. What's the same? What can we multiply by? 9/5. Good. So we're going to multiply both sides by 9/5. And so that gives us 9/5 y equals x minus 32. And then what? And then add 32 to the other side. So we have 9/5 y plus 32. And that is the way to calculate the other way. And this is kind of funny because I have friends in England and they are Celsius. They're not Fahrenheit anymore. And so one of my friends, who's also a math major, she just kind of, that's what she does every time. I tell her what the temperature is. Roughly. I mean, it's always like a rough approximation. It's not perfectly perfect ever. So we got 9/5 y plus 32 equals x. So there we go. And then you can hit share with class if you want. I like to do that because then it's fun to see everybody's responses. And then you got like people's response. Okay, so next, it's heating up. So now we're gonna have this, we're gonna put it in function notation, and so it produces Celsius temperatures. In addition, let f of y be the function that converts a temperature given in y degrees Celsius to temperature f of y. Okay, so all this is saying we're just gonna write what we did before in function notation. So to calculate Fahrenheit, so f of y equals, and then what did we get in the last screen? 9/5 x, oh y, thank you very much, plus 32. And that is, now it's the same formula we had on the previous screen, it's just now it's in function notation. So Fahrenheit as a function of y. Now the reason we're writing them as functions is because we're going to think of these as inverse functions. So the inverse is when, I mean, we did that algebraically where we'd swap x and y and then solve for y again. We didn't swap them, but this is the same idea. We isolated the other variable and turned this into a function of the other variable. Okay, next. Now, find the value of c prime and f prime. How do these values appear to be related? So now you're going to go back to C. So if I have to scroll back, there's C. So find the derivative of that. 5/9 is a constant multiplier, I would just like to point out. Bless you. Well, it is a line, right?
Oh, okay, that makes sense.
So what's the slope of the line?
It's 5 minutes.
Yeah. Yeah, I am. I am.
Oh, we can't come into that.
Oh, yeah.
Okay. And then what about f prime of y then?
That fits.
So the slope just goes. Okay, wait, don't.
It's just 9/5. Now, okay, so let's just talk about like implicit differentiation right this second, because we've been taking derivatives of y and then putting y prime on the end of it. This is the derivative of f with respect to y. which is the same thing as the derivative of c with respect to x. So I know that's weird, but now y is the independent variable and f is the dependent variable. So when we take that derivative, we're just gonna get the 9/5. There won't be the y prime on it. So when we're taking the derivative of something with respect to whatever its variable is, I mean, if you want, we could put t's in here instead. So you would have f of t equals 9/5 t plus 32. And so when you do f prime of t, you'd still get 9/5. It's like whatever that independent variable is, that's the one that goes on the bottom. And so that's the thing we're taking derivatives with respect to.
Because I thought the constant multiple rule, you just took the variable to find the derivative. Like,
Constant multiple.
like if you had 3x
Right.
plus 32,
So,
it would just be x.
no, it'd be 3.
Well, but for f of y.
Yeah, so it's just 9/5. It's just a constant multiple in front. Because it's y to the first power. And this is one thing I'm not sure I like about this one. Because now we're like, why is it
What?
Because I thought you would have to use the chain rule, because then you leave the inside. I don't know, but so you don't do that?
for C or for F? Let's start there.
The bow?
Okay, so let's do C. Alright, so if we want C prime of X, we got this constant multiple on the outside, so it just stays along with us.
Yeah.
And then what's the derivative inside?
It's 1.
It's just 1.
Okay, but when I thought you would use the chain rule, and then because you would leave the inside time.
Okay, so if this is to the first power,
Yeah.
when you bring this down, you have 5/9 times 1 times x minus 32 to the what power?
To
0 power. So the 0 power, anything to the power of 0 is 1.
Okay.
And then times the derivative of the inside, which is 1.
Okay.
So it'd still work out.
Okay.
It's 5 minutes for that one. Okay? For f prime of y, I'm going to take a moment and I'm going to write this the other way. I'm going to write df dy. So I want the derivative of f with respect to y. See how it's on the bottom now? Usually we say dy dx, and dy is on the top. And so here in this situation, if I take the derivative of f, I get df dy. So if f is implicitly defined, if I had like an f squared somewhere, then when I take its derivative, I would do, like I do a chain rule to f times df dy.
F is our new y.
Yes, f is the new y. So when we take the derivative of that thing, which was 9/5 y, wait a minute. So f of y, we just wrote that, 9/5 y plus 32. So when we take the derivative of that, we just get 9/5. Okay, and then the question is the connection. So what do you notice about the derivative of C and the derivative of F?
Perfect. Yeah, yes. I like that.
This one's 5/9, isn't it? And then this one's 9/5. And so, what do you notice about these two? They do, they multiply to 1 because what are they in relation to one another? It's a better word, somebody said it, reciprocals of each other. They're reciprocals of each other.
Reciprocals, you flipped it, but you have to, it's a negative.
Oh, no, that's an opposite reciprocal. Opposite means change the sign. A reciprocal means flip it over. So this is just a reciprocal. Yes?
What is the difference between reciprocal and inverse?
Well, so when we're talking about inverses, we're talking about like an inverse operation. And and in fact, they don't even call it the inverse function anymore, the 1 over x. They call it the reciprocal function because it flips it over because there was a lot of confusion there. But inverse operations undo what's been done to the variable. It's like undoing things, whereas a reciprocal is just flip the fraction over. So Yeah, because if we had like x plus 2 and you had to get rid of it, you would do the inverse operation, which is to subtract 2. That's not the same thing as flipping it over. And that's where I think the confusion lies. But they're reciprocals of each other. When you multiply them together, you get 1. That is actually the definition of reciprocals, is that when you multiply them together, you get positive 1. So there you go. And this is kind of a big deal because remember, we talked about switching x and y, right, with functions, inverse functions. And so with an inverse function, we switch the x and the y because slope is change in y over change in x. And then we take it, flip it over, and now it's the change in y, like it flips. They change spots, so they're reciprocals of each other. This is the big deal that I was trying to build here, so let's see. Inverses. What is something you remember about inverses? Ooh. Is this multiple choice here? Oh, no, it's not.
I think the answer is inverse.
Oh, I see. Explain
The
anything.
thing is, like, how
I'm just looking at what they have here. An example of 2 inverse functions is... Oh, we did this already.
yeah.
Inverses, never heard of them. All right, so we did this yesterday. In our web that we went through and put all the things that we remember about inverses. So we're good there. So we're gonna go to the next one. Mirror, mirror. These 2 functions are inverses. Play with that floating point on there for a bit. What do the points have in common? So it would be nice if these locked. So you can move the point around, and as you move the purple one, what happens to the blue one? It follows as well. And so it goes along the curve, and I wish I could get it to tell me another curve.
The coordinates are inverted though.
What do the points have in common?
They're inverted.
What do you mean?
The x and the y switch.
So they have the same x and y coordinate, but they're switched. Yeah, that's just what we've talked about.
Are they inverses?
Yeah, they are.
Yeah.
It says they are,
Yeah.
so we're gonna go with it.
Oh.
Yeah. It says these 2 functions are inverses, and so what do you notice about? I like this ordered pair here on the axis. That's kind of nice because you've got x is 2 and y is 0, and then if you flip that, y is 2 and x is 0. So you've got a coordinating point there. There's another one. I don't know if I can get it there. Right there. So this point appears to be 12, 2, and then over here, it's 2, 12. So there's your flip-flopping. Why are these functions inverses of one another? Well, what is the function? We can actually write this equation. Start with the red one.
X cubed plus 2.
So the red one, y equals x cubed plus 2. It's our cubic family. It's just from the shape of the graph. And so if we do an inverse function, remember we would go like this.
X cubed.
And so we'd subtract it off. And then we'd cube root. So the cube root of x minus 2 equals y. And so we can see this one is our cube root. Remember we talked about vertical tangents. So that's a cube root to the 1/3 power. And it is moving to the right too. So this is our horizontal translation now. And so that's why they're inverse functions. Now, really why they're inverse functions though, is if you take these 2 right here, those and that one and that one, and if you compose them one inside of the other one. So in other words, if I take this stuff, I did change that to highlighter, right? Just, everybody saw that. Okay, I'm on highlighter.
More.
All right, so if I take this stuff and I plug it into x cubed, because that's what it means to be an inverse function. I'll show you. So if we plug one inside the other one, so we've got y equals, and then we plug in the cube root of x minus 2, and then we're gonna cube it, right? That's this right here. And then plus 2. Well, what happens when you cube a cube root? It cancels out, so we just get x minus 2 plus 2, and then what?
Equals X.
Inverse operations undo what's been done to the variable. It undoes what's been done to the variable. So if I like look at these two functions and I plug one inside the other one and I end up with x, I've undone everything that has been done to x. So how did we get this thing alone? We subtracted 2 and then we cube rooted. That's how we got it alone. Subtracted 2 and then cube rooted. Subtracted 2 and then cube rooted. That's what makes them inverse functions. They undo each other. That's the difference between inverse and reciprocal. Reciprocal is just flipping things over. Inverse is actually undoing what's been done. So, all right. Mirror, mirror. These functions are special symmetry. Ooh, you can sketch the line. Sketch the line of symmetry in there. Line of symmetries always go in between coordinating points.
There's a line function.
Oh yeah, you can do that one too. So I know it's gonna go there. Oops. Oh, yeah, okay. Oh, boy. Here is. When things are symmetric, the distance from that point to the line of symmetry is always the same on either side. It's always perpendicular as well. The line of symmetry will go through the perpendicular bisector. We're doing a lot of that in geometry this year. Our new geometry stuff. Yeah, it goes right through that perpendicular bisector between those 2 points. But anyway, so we got that. That's our line. Just write it. Y equals x, where all these ordered pairs are exactly the same as we go through. And that's why right here they match up, because they're right on that line of symmetry. So it's like -1, -1, though it's probably not quite that, it's a little above that. Okay, now, ooh, this is nice too. So now we're talking about tangents, right? We're going back to calculus now. And so we can drag these tangents around here. Point of tangency, there's our tangents. What do you notice about our tangents?
The slopes are inverse.
The lines themselves are reflections. Look at those lines over the same y equals x. This is different from our worksheet, that's for sure, because we couldn't move points around. But when we talk about inverse functions and their derivatives, now we can relate their slopes. And so it's kind of a tricky spot, because notice that these 2 points have to be coordinating points. And then we can talk about slopes. So the hard part is it can be helpful for formulas and things like that, but it's very, very specific as to where it works and where you wouldn't want to use it. So we're going to use it a lot where you have those coordinating points. We're going to use it a lot where to find the actual inverse function would be tremendously awful. And so you wouldn't want to take its derivative. So for example, I think that's what comes next. No, I'm going to go over here. So for example, we're going to look at things like f of x equals x cubed plus x squared plus 1. All right, if I try to find the inverse function for that so I can find its derivative, yeah, that's not a thing. I mean, you'd have to swap the x's, turn it into y, swap the x and y, and try to solve it all around, and that doesn't work. So we get around it because we know that, so if we have f inverse of x, so I don't know if you remember that notation, and we want to do its derivative, then we know that it's 1 over f prime of x. But this is weird though, because we've got to talk about this coordinating point. Those x's aren't always the same thing. They're coordinating. That doesn't make sense right now. All right, I'm sorry. I'm doing this new. You're like, wow, I wish we'd done the other worksheet. Oh, no, it's okay. We're gonna take some ordered pairs now. Ooh, look, it's labeling the points for us, so that's really nice. So we're gonna go to this point right here, -2, -4 on the red graph. -2, -4. So I'm gonna pull this point down, maybe, yes. There we are. And it sort of snaps on there for you. So on the red graph, which is the blue point, I should change that. But anyway, on the red graph then, at -2, -4, we need to find the slope of this line, or the red line. I'm going up very steeply. How would we find that slope? So we got a tangent line. Here it is, it's this red one. And we know one point on the tangent line. If we found another point on the tangent line, we could calculate its slope. Right? So, how's everybody doing right now? I don't know how you're feeling.
Pretty good.
Are you okay with this? Are we doing okay? A little weird. Okay. So we're going to take this line right here. We're going to find its slope. Right now it's the tangent line that goes through -2, -4. So we know that much. It goes through the point -2, -4. We need one more point to find slope. So if we look at this and we follow it along, it appears that it goes through that point right there. So we're going to give that an ordered pair. So that's -1, 8. Or, sorry,
9. Isn't it?
9, sorry, thank you. I was pretending to count by twos, but it's not counting by twos. Is everybody good now with my ordered pair? All right, how do we calculate slope?
Yeah, I want 2 minus 5.
9 minus -4 over -1 minus -2, which is 13 over 1. Okay, so our slope is 13 right there. Do I have the right ordered pair? Alice, is that working for you? So it's counting by ones. On the last graph, it was counting by twos. So this is 5, 6, 7, 8, 9. And then, I mean,
Alice is looking at this one, -1, 8.
oh, -1, 8.
That's what it looks like.
Oh, that's.
This is just.
Okay,
This is
no,
just
I-
an approximation, so
I think he's, well, yeah, we're looking for something, so it might be helpful to do that.
It's -1, 8, and it's on.
Thank you. So, let's just change his things here. Let's fix that up. So 12.
Is
Is that better? Is that better?
Yeah.
Okay, phew. All right, now we're gonna look at the orange graph. That line right there, what's our prediction? What do you think the slope should be? 112. So, we're going to try this out. So we know we have the ordered pair. We know we have the ordered pair. -4, -2 this time. And if we go through here, they're inverse functions. So it should be that one, right? It should be, what should the other point be? 8, -1, because they should be flip-flopped, right? If they're inverse functions. So now we can do this as our slope. So -1 minus -2 over 8 minus -4. And so we end up with 1 over 12. Inverse. Now, this only works though, again, if you're at coordinating points. So this worked because we were at this point and then the coordinating point to it on its inverse function, which is the one where you flip-flop it around.
Don't we always know the coordinating point?
correct. Fact. But the way they ask, it's a little wonky sometimes. So that's why I'm just establishing that idea that you have to be at the coordinating point, and then you can calculate the slope and play back. Okay. I think we're ready for, let's see what else is next here. 12.
Why didn't we just use some points?
I don't want to do that.
Oh,
I think we're ready.
it was the
Well,
tangent
I think we're
line.
ready.
True. Which of the following are true?
It was supposed to be the line being silly.
Yeah, we're ready for this one. We're gonna go to the very last slide on there, and we're gonna talk about this. So, the way you're gonna see this, like on an AP exam, is usually through a multiple choice question, or like on my end of the unit test or something like that. It's going to end up being multiple choice, and so this isn't quite multiple choice, but you'll see. Like I have a special assignment for you, a worksheet. Worksheet. It's not very long. Just that sort of practices these situations. So the first part of this says, for function f, we know that f inverse of x equals g of x. So all it does is establish that f has an inverse that is also a function, and we're going to call it g. That's it. Then we also know that f of 3 is -1. F of 3 is -1. All right. So what does that mean for the inverse? So if f, every time, f of 3 equals -1. What does that mean for the inverse?
That f of -1 equals 3.
Sort of, that f inverse of -1 equals 3. Or in this case, what do they call f inverse?
G.
So g of -1 equals 3. This is the first thing to establish. That's why I kept saying these are the corresponding points. So on the original function, it was 3, -1. On the inverse function, it's -1, 3. You flip it around. Okay. Then, we also know that f prime of 3 is equal to 10. The important thing right here is that this, yes, okay. So, sorry, not important thing. F prime of 3 is equal to 10. So, what is the corresponding point then for the inverse function? This one, right? That's the corresponding point. So what this tells us is that g prime slowing down, g prime of -1 equals. So check out this correspondence, this relationship here. So first off, we established that we have a function and that function has an inverse function. There we go. We're gonna call the inverse g. So if we know an ordered pair on the original function, we know that corresponding point on the inverse function. We take the original one and flip it around. So far, so good. All right, so then this relationship that we've been exploring says that if we know the derivative at that 3, if we know the derivative at the original function's point of correspondence, then we know the derivative at g prime of -1, because that's the corresponding point, and we take it and we just flip it over.
Yes.
So, let's try this again. Let's say, let's go to this equation where I had f of x equals x cubed plus x squared plus 1. Yeah, probably. So the first thing I'd like you to do is find f of 1. You can plug it in your head if you like. What's f of 1?
3.
3, okay. So then, f inverse of, now what would we plug in for the inverse? Flip it around, so f inverse of 3 is equal to 1. So we could flip it both ways. Alright. Now, what is f prime of 1? So how would we figure that out? We need to take the derivative of f, so f prime of x equals 3x squared plus 2x. And then we can do f prime of 1. So that would be 3 plus 2, which is 5. So far, so good? Alright. So then, when I ask this question about the derivative of the inverse function, I'm going to say, what is f inverse of 3? The derivative at that place. So what is the derivative of f inverse of 3? So you say, well, the value of f inverse of 3 is 1, which means that its corresponding point on the original function was 1, 3. So if I find the derivative of the original function at 1, then I take that and flip it over, and that gives me the derivative at the corresponding point. It's very funky, and that is a funky notation. So, I apologize. It's terrible. Like, because I feel uncomfortable with this because I feel like this should be a constant. When you take a derivative of a constant, you get 0, which I put notes about that on your assignments. But anyway, but when we're talking about inverses, there aren't a lot of fun, and that is one of the reasons why they say let's let f inverse of x equal g of x, and then for here you would just write g prime of 3, and then, so it looks nicer. What do you mean? I just did that.
Take the big parentheses out though.
And put the prime where? No. Because you're not taking the derivative of 3.
No, but you take the derivative of f of 3.
I don't know, Travis. Look it up, dude. It's notation. I can't change it.
No.
Nobody will let me. So,
Okay, how did you get it again? Because
so it's that corresponding point here,
Where's one?
1, 3, and then this one goes with 3, 1. So if I find the derivative at 1, then I flip it over, and that's the derivative of the inverse at 3.
So it's like 1 when you plug it in, f of 1. Is that's like given to you? You didn't just like pull that out of nowhere.
Well, we figured out.
I just plugged 1 into this equation.
Just-
Yeah.
just-
Somehow you got to know.
Like on the test
It's very
board.
specific, so you have to know where you're going with it. You can't just.
So like they can't just give you that and be like,
So-
yeah, I figured it out.
If you have to find like the derivative of the inverse, you're gonna want to go back to the like original value that you plugged in, find the inverse, and then okay,
Yeah, so
Okay.
you need a point.
Yes.
okay. Travis got what I
Okay.
I understand the argument.
Yeah.
Travis is like the translator.
Alright.
Translator Travis.
So,
Travis
okay. So I think this is a good time to come back to the fact that when we talk about inverse functions, so if we would say that f of g of x, so this becomes a composite function, f of g of x. So when we compose, or we put one inside the other one, if g is an inverse of f, then the answer to that will have to be x, right? Because the inverse function undoes what's been done to the variable. Okay, so let's take a moment to think about that. We're good there?
Yes.
Inverse function undoes what's been done to the variable. So, take the derivative now of both sides. So on your assignment, number 58, you had to do derivatives like this. So, it's a chain rule. So what's the derivative of the outside? F prime, leaving the inside alone, times the derivative of the inside, which is g prime of x. equals, now, what's the derivative of x?
1.
1.
Tice Mills and Candace Goodrich. to
Now
the
get G
opposite
prime by
is
itself.
Tice Mills and Candace Goodrich.
1 over f prime of g of x. Remembering that that is the inverse of f.
Oh, so then it's just flipping it.
So the derivative evaluated at the output of g.
Okay.
So we can look at that a teeny bit more tomorrow. I'm gonna give you your worksheet. You can try and do a little of these. Some of it's multiple choice, some of it's show your work.
There's a really good Khan Academy video.
There's a really good Khan Academy video on it. I screwed it up.
No, I'm just saying.
No.